Thank you, Chris. So 9 a.m., Wednesday of SIGGRAPH. You folks must really love real-time ray tracing, so I appreciate you all coming out. So I have a sense of who's in the audience. Can you raise your hand if you work on sort of CAD, DCC, visualization? Okay, yeah, visualization, yeah. Film previs or production. Okay, so that's good representation. And games industry. Oh my God, okay. So I made the right call when I set up the slides then, which is, I think for the people who weren't in the games industry right now, it's obvious to you what real-time ray tracing means to your pipeline, and it's obvious in some sense how to start integrating it. And I think for game developers, so the technical side of this is going to sort of apply to everyone, but the pitch is sort of phrased for game developers. And the reason for that is because game developers have really extreme performance constraints compared to other real-time industries, and usually relatively low hardware compared to what you can enjoy in like a Maya workstation or something. But the key is actually not the performance side. It's the difference from game developers is that they have artists. And what a game graphics programmer knows is that the game graphics programmer's job is not actually to make games look good. Right? That's the artist's job. And what the programmer's job is to support the art team. And in order to support the art team, we're essentially making paintbrushes, right? They're very cool digital 3D paintbrushes, but that's sort of what we're providing are the tools. And so the question that a game developer is coming to today's content with is, is this ray tracing paintbrush, is it really good enough? Is it something I need? Is this really a sufficiently better paintbrush to start upending my pipeline? And then if so, how do I put that into a real-time pipeline? So what's the process? Not the end game, but how do I get to the end game? And so this will apply to everyone, but I think if you're a game developer, that's the perspective I want you to come to this content with, is how does this help my art team? And in that context, I'm going to give you sort of a story of the recent past and what I think is probably going to be the very near future of game and real-time graphics in general. And I want to acknowledge that there are many, many people who helped me make sure that story is mostly nonfiction that I'm about to tell you. So they're the folks up here, and they give a lot of feedback on sort of the ideas behind this talk. And again, if you're in the games industry, your first reaction should be looking at sort of the affiliations. You're like, wow, these guys are brilliant. That's wonderful. Like, I don't have to believe Morgan. Somebody who knows what they're doing is talking about this stuff. But you're going to say, games aren't films. And that's a really critical point. The games are not films. We're not going to do what the film industry did, but we can learn from it. So games have fixed frame budgets. You can't manually post-process every frame. You have a post-processing stack, but it's fixed. And you have these annoying things called players, and they run around and they affect the lighting and the camera and the action and stuff. And the visuals are ultimately also subservient to gameplay. And so in film, there's a notion of here is what the director wants to show the player. And games come from a perspective of here's what the player wants to see in order to accomplish a task. And so we use a lot of techniques in common, but there are some sort of key differences there in how you structure a game graphics pipeline and the constraints you have. And so hopefully it'll be clear in about 3 slides why I talk to all the film experts about a pitch that's going to go to game developers, but that's somehow technically relevant to everyone. And to sort of set the stage for that, let me give you a timeline of games in 4 slides. And keep in mind as you look at this that it's not about the technology. It's about the technology as a piece of a production workflow. And that's the aperture which I'm looking at this content. So, my beard is just long enough that I did some game programming before 1999. And I sort of think of that era from the sort of dawn, the real renaissance of video games up until 1999, which is when the GeForce 256 came out, as sort of its antiquity and sort of, right? This is kind of Pac-Man through Half-Life. And in some sense, and this is one of those uphill both ways kind of stories, having coded in that era, I feel like, that was when the important stuff in games happened, right? That was when games rose to the point of equaling and today probably surpassing film in terms of at least economically in the industry. And so it was really important, and kind of if you programmed in that era, you were a hero, because it was really hard to make pixels show up on the screen, let alone make good-looking pixels show up on the screen. So it was super important, but I think that era tells us a lot about gameplay, but not a lot about modern game production pipelines. And so we're going to appreciate that, but sort of leave that in the past. And then the era that we're in now, and this is sort of after the advent of programmable shading, is a little bit of a different story. So once we had programmable shading, now we had real production pipelines. We had a lot of control over the rendering look. And this changed everything about game graphics. And regardless of whether you're a game developer, because this is where we bring everybody back in, the words up there are probably not old friends, but they are colleagues, maybe the colleagues that you don't like. Like, how much time have you spent tuning shadow map cascades or dealing with pre-filters or fighting Z-fighting? But this is the world that we live in today. And you'll notice that I have like a tombstone end date on this era, right? Which is Monday, last Monday. So it's time to move on. So this is the era where essentially we can put any image we want on the screen in a game because the artists are that good and the programmers have enough flexibility to support them. But we're straining it to the breaking point. It is not fun to do game graphics anymore, right? The reasons you got into this field 5 or 10 or 20 years ago, you're now spending all your time sort of debugging the edge cases because there's no room left in that pipeline. And so I call this sort of the Raster hero era because it is tough to get any innovation and then somebody keeps cranking you up from 720 to 1080 to 4K, and they somehow want the game to look better when you have 4 times as many pixels on the same platform. But the games look amazing, right? We are at the point where enough artist time on a hero shot and enough programmers working the shaders, and you can make any image you want today. And it's a wonderful time to be a game developer and a game player, but how do we go beyond that? And what is about to happen, what started Monday with the release of an announcement of Turing, is that we're moving into a world where you take your current raster pipeline and it sort of coexists with an emerging ray tracing pipeline, a real-time ray tracing pipeline. And there are some places that hopefully the second you heard ray tracing is fast, you started thinking of all these kinds of places in your pipeline where you probably already have some ray tracing, either at runtime or offline, and saying, oh, that just got 20 times faster. Right? So that piece of the pipeline, not the whole thing, but the part where you're already ray tracing is faster. And that sort of coexistence. And see, here's the interesting thing about this, and this is why I talk to the film industry. So the point that we're at in 2018, the code that you're about to go back to your office and write next week that takes advantage of Turing and DXR, that code basically corresponds to the place that the entire film industry was at around 1998. So this is sort of Pixar releases A Bug's Life, 1998, and it's a mixture of rasterization, micropolygon rasterization and RenderMan, with ray tracing added on top. And that's exactly what we're about to do with all of these features. So notions like, oh, now my baking goes a lot faster for the lighting because I can hardware accelerate it on the lighting server. And you know what? I don't have to do like weird fiddling with shadow maps. If I have a point light and hard shadows, let's just ray trace them. And it's obvious how that drops into your pipeline. And this is really exciting. And at the time, this was an amazing looking film. And I think it holds up today. But the challenge is this hasn't solved the production problem. Right? Today, with screen space ray tracing and environment probes and baked lighting, I can make that image in a game already. Ray tracing is not giving me more image fidelity. What ray tracing is going to give you is a way to change your pipeline so it's not at the breaking point anymore. It's a way to do exactly what happened to film, which is they said production at this point with an entire raster pipeline and a ray tracing pipeline on top of it is not sustainable and we can't innovate on the look. And 10 years after this point, every company that works in film and VFX was moving to path tracing. They're moving to embracing a ray tracing only pipeline for production reasons primarily, because it unlocked what the artists were doing. It was what the programmers did to give the content team the leeway they needed. And today, that's complete. So there are almost no raster pipelines in mainstream film production today. And I think we're going to do the same arc for real-time rendering, but we're not going to use the same answers, but we're going to follow the same path. And it's because we have slightly different constraints. So what I think is going to happen, and we've been working on with several partners that you're going to hear from today, and there's a lot of research that we'll talk about in the second talk, is that there's this transition period where we have a Ray pipeline and a Raster pipeline, and they're kind of coexisting happily. And it gives us a few new effects, and it starts to streamline a little bit of baking. But what we want to do is get as fast as possible to this golden era. And unlike film, I don't think we're going to ditch Raster, at least not for a very long time. But I think there's this world of native Ray Raster hybrids where you use rays for what rays are good at, but you keep the rasterization pipeline, you keep the screen space effects for the things that they're good at. And that will let you have the dynamism of games, it'll let you have the flexibility, but it'll also let you have the production workflow that you need in order to innovate into the future. Yeah. So that's what I think takes us in games from visuals that are like A Bug's Life to getting somewhere, a modern CGI film like Coco. And when you look at this image, think about not the image quality, because you can render that today, but think about the production cost of being able to render that. And what my colleagues in the film industry told me is that when they transitioned to a new pipeline where it wasn't raster and rays bolted together, but something that was redesigned around the technology of the day, that gave their artists a 2 to 5 times speed up. And you take that speed up and you put it where it counts, which is on the screen. And so now you can model better, you can animate better, you can light better. So you end up with the visual fidelity, but not because of the runtime technology. You end up with the visual fidelity because you allow your artists to be superheroes. Okay. So that's sort of the big picture. Let me tell you how you get there, because we've thought a lot about this. So here's the roadmap. The first thing you need to do, and this is literally today, Turing exists, you're going to be able to buy one very soon, the APIs are already out, is you need to take the pain points in your production workflow and you need to redesign those right away for ray tracing. So if you've got baking in your pipeline, if you're making light maps, if you're baking ambient occlusion, it's pretty obvious what you're going to do. So those probes and those light maps are going to be ray traced, but they're going to be ray traced with this huge speed up, so your artist doesn't go off and get lunch. When they push the bake button, right? They push the bake button and they start to stand up. Oh, it's done. Oh, well. I guess I'll have to do another iteration instead of walking away for an hour. So accelerate baking to pretty close to real time. It's going to be sort of interactive viewport level real time now. Start looking at the pain points in your VFX compositing. Start looking at places where it's, I have screen space rays and they work pretty well for reflections, and then there's all these horrible corner cases. Well, take the corner cases and don't try and fix them in screen space. Trace the screen space ray just like you're doing, but then from your DXR shader, you just launch a true world space geometric ray. And it just unlock that production. Don't tell artists like, oh, the reflections don't work at the edge of the screen, so you have to put a rock next to the water so that no one can see off. They don't need to worry about that anymore. They make the scene they want now. And then start revisiting assumptions. As we retooled our pipelines internally at NVIDIA, to go to ray tracing, we found all these places where we made assumptions about the raster pipeline and that we're actually constraining things, that we're making it so there are all these places where the effects broke. So things like, I assume that pixels that are being traced in adjacent threads are actually next to each other. And maybe that's not true if you're starting to do sparse rendering or probe rendering or something in the future. Making assumptions about filtering, anti-aliasing. And the big one, of course, is this notion of static versus dynamic is a totally different thing in a world where you have GPU-accelerated BVH refitting. So don't change those, but start ferreting those out as you go through your code base. And then you want to get as quickly as possible to what I'm promising you, which is this hybrid rendering. So not a full path tracing pipeline, not games are going to be film renderers, but redesign your pipeline so that each piece does what it does well. And you want to design, in general, visual effects around ray tracing. You want to think of it first in sort of a mathematical, pure way. So if I have a reflection, oh, that's a ray trace. Great. I have ambient occlusion. Great. I trace 20 rays and average them. And that gives you the robustness. And again, this is really about the content team if you're in game production. But if you're not in game production, it's sort of even more important, because if you're doing a CAD system or something, there is no artist who will fix the image to make it look good. Right? The program somehow needs to render it correctly when you didn't know any of the parameters for the content. And in that case, robustness is essential. That's your whole life. You can't use an effect unless it's going to always work on all kinds of content. And we've already, as an industry, moved to physically based materials. And the reason for that wasn't photorealism. It was to get predictability and robustness, to get things that are stable if an artist or a player does something unpredictable. Physically based materials get you halfway. The next step is physically based lighting. And physically based lighting means ray tracing. It's the only way we know to do it as a field. And then what you also want to do is leverage screen space. So don't throw away the screen space tricks you've used, but use them in the places where they work and they accelerate computation. And then keep all the good stuff that works at a high level. And a lot of this is stuff that, again, film doesn't care about because they don't have quite the same production constraints. And my favorite example is just tile-deferred shading. Right? So we've spent a long time as a field getting to the point where you can have hundreds or thousands of lights in a scene, but we bin them carefully so that only lights that affect a pixel or a few pixels will actually be processed there. That idea has nothing to do with rasterization. That's a really good optimization that you can use with ray tracing. And you can still conserve memory by streaming textures and geometry in. And you can still do all of the great things you're doing in screen space for filtering and post-processing and color grading. So keep that stuff. You don't have to give up any of that. But throw away the things that were kind of hacks that are holding us back and screwing up the production pipeline. And the last one, and this is sort of how you scale to the future. So I gave you sort of 2018, 19 to 20 is sort of the hybrid pipeline. And then what's going to scale way out to the future, so you need to start learning it today, even if you're not implementing it, is learning how to get as much information as possible out of a ray. Okay? We made those rays very fast at NVIDIA. You're going to see these sort of 5x to 20x speedups depending on what kind of shading you have. But they're not free. You still have your 16 millihertz, millisecond or whatever budget. So you got to get as much as possible out of every computation. And so the best description of this was actually in Matt Farr's book, Physically Based Rendering, and in the course he gave on Monday. And I'm going to reference those notes. There's this concept of importance sampling, and it basically means get as much information as possible out of each ray so that you spend sort of constant compute time for every amount of incremental visual fidelity. And there's actually math that tells you how to do this, and it's in his book. And then there are ways of sending out rays and sending out samples, whether it's in screen space or world space, that will do surprisingly powerful things if you follow a couple of patterns. And the last is be aware of this revolution in reconstruction technology, in taking those samples and not thinking of the rays you cast as turning into pixel values and doing what for a long time film tried to do and they've kind of started to back off from, which is you get a couple samples and then you trace 1,000 more rays to try and get rid of all the noise, and saying, no, after like 2 samples, it's basically there. I can see what the image is going to be, and is there a way to take that as input to a final pass rather than treating that as the final pass and grinding it? And I think this story is best told through pictures. So these are from Matt's real-time advanced real-time rendering slides. They're going to be online and tomorrow, I think. And you can see the math. And really, at some point, you're going to have to bite the bullet and read his book. And it's kind of a heavy book. But while you're waiting for your Turing to ship, you can read the book. So this image, this is a bunny. It's on sort of a ground plane, and it has very few samples. I think there's 16 samples per pixel to do everything, the lighting, the shading. And I'm going to take those same 16 samples and get this image. And so see how a lot of the noise, the shadow's still noisy, but a lot of the noise goes away? Those have the same compute time. And it's about a 2-line difference in a shader to get between those images. Okay? So that's probably math you want to know. And in fact, there's some other really extreme examples that he gave. So this is 4 samples. That's the same 4 samples. So putting your samples where it counts matters. And then, that's still a grainy image, and that's where there's a huge number of different denoisers. Some are published by us, some are by others. I'm going to give you a few references in the next talk. And they can take those noisy images and get you to the final result directly. So maybe 2 or 4 samples is actually enough. And this isn't magic. It's that the information content is there if you put the rays in the right place. Okay. So in this talk, I've told you sort of what topics you need to be aware of. Obviously, we don't have enough time here to tell you the answers. So I'm going to tell you where to go to find the answers. And so the first is sort of recommended reading of resources. That there's a number of university professors who saw this revolution coming, and we were really excited to join NVIDIA. And we've essentially all written short books that are something you can go and read through in a week or 2 weeks that will tell you what you need to know to start adopting this technology. So this is, if you want the crash course, this is where I would go for those. And then there's sort of the slightly heavyweight. Now everybody works in NVIDIA now, so these are also NVIDIA authors. But I'm showing them to you because I think these are the books that are accepted. The film industry gave Matt an Academy Award for writing that book. So this is where you want to go to get the hardcore math. But these are books that are going to hold your door open for you and stuff. So, and then what's super exciting is there's sort of this love letter from the future. The film industry has documented for us what their production pipelines look like. And this just came out last week. And so ACM transactions on graphics, and there's a few other earlier works that tell you about all of the missteps they made and all the clever things they invented to move to ray-based pipeline. And I don't think we want to do what they want to do, but I think we want to learn from it. So in summary, what I want you to take away from this talk is that every 20 years, consumer graphics technology has a revolution. And it's driven by games, but it comes to every aspect of real-time rendering. Okay? And this is, it's only happened 4 times, so I don't know if you want to put your money down on 2038 now, but it's time. This isn't business as usual. This isn't a small bump. This isn't the next product cycle and a tiny feature. Okay? This is, today, real-time ray tracing and Turing. It's like in 1999 when programmable shading came. Can you imagine? I mean, think about what happened to the companies who said, "Oh, I don't need programmable shading. It's a fad. Hardware TNL is great. That's all I need. Garot shading. It's going to be beautiful. I got some register combiners. It's really wonderful." Those companies don't exist. The ones that bet that way, and the ones that said, "I'm going all in on programmable shading." Those are the companies that seized that moment, that became huge, right? And this is where we got to today, and we have now Epic and Unity and all these great engines out there because they embraced programmable shading, because they saw that the world was about to change. And it's tough because this only happens once a generation, so you sort of need somebody with a beard maybe to just say "Oh, I made the wrong mistake last time. Let's not do that mistake this time." You need real-time ray tracing. You need it in games. You do not have a choice. This is the way the entire industry is going. And you're here on day one, so you have a chance to get out ahead of the curve, and you need to seize that. So that was the history. My roadmap is straightforward. Today, refactor your production. Take places where it makes sense to cast rays and it doesn't upend the real-time pipeline, and just do it. And you're going to get this huge speed up, and it's going to make your artist 5 times more productive. And then start for your next title embracing hybrid rendering. Start redesigning your pipeline for where we're going to be for probably at least 10 years. Probably a lot longer, which is this notion of raster and rays, each doing the thing they do best. And then, once you've got those rays in there, you have the hybrid rendering, start realizing there are places where you can get another 10x, not from hardware, but from math. Right? Start adopting the algorithms and the hard sampling ideas that have been worked out for us very carefully by the film industry, and then add the new real-time denoising techniques on top. And at the end of the day, this is not just graphics even. Right? Start thinking about where can you use rays in virtual reality? How can you lower latency? How can you sample sparsely, do barrel distortion? How can your AI use rays to get true visibility instead of pre-computed and take your map and you kind of grind on it? How can I actually just use rays to stab and say exactly what can this AI see? What can it hear? Where can I use ray tracing in physics? So all my particles essentially, they're just little rays over one frame time, and I can have perfect collision detection for particles. So I think there are a lot of opportunities in interactive technology for these. And if you take home just one thing, remember that ray tracing is, in a sense, not about you if you're a programmer. It's you get the shiny spheres. Yes, you can do shiny. Chris made these amazing real-time shiny spheres. They were beautiful. But that's kind of the hello world. That's not why you're doing this in production. The reason you're doing it in production is because this makes everything robust and physically based, and it lets you get whatever look you want, but in a predictable way that's efficient. And that's ultimately about making sure that you have very productive and very happy artists. Thank you very much.